Okay, this is the equation, which is R is equal to 2 mv q divided by q and b squared under the root. Okay, what is R? R is the radius. What radius? Radius of this arc, this circle. Okay, as I told you that this is the circle, it is moving like this. Okay, this is because it is deflected. As let me tell you one thing that I already mentioned it, that I cannot draw a three-dimensional thing on a 2D board, so it is quite difficult for me. So if it is moving like this, okay, this circle, it is equal to this thing, it is coming toward you. Okay, it is very difficult for me to write to on two-dimensional board. So this curvature is like this. Okay, this circle. So it is the radius of arc. This radius could be big, could be small. What does I mean from the big? This is one radius and this is other radius. This is big, this is small. So how what the radius means, let me tell you that we have to write those things. Okay, let me use the black pen. Suppose this is a radius. If some particle is moving here, it is a big radius. Okay, now the blue one, it's a bit now look at this. This is a bit smaller, and you will come to know that what these things are. Now R is the radius, m is the mass. Okay, of what we don't know, but it's the mass of the radical cation or the positive species. Okay, v is this potential difference between those plates, or the voltage applied, okay, across these, that how much it is pushing and how much it is pulling. So it is some volt. Okay, maybe it is 60 or 6000 volt, or 2000 volt, or plus minus something. The pushing of the positive charge and the pulling of the positive charge to make them accelerated, to move them faster. So this is the V. Q is the charge on the particle, or on the ion. Okay, as you know that in electron ionization, most of the ions or molecules, after bombarded by the electrons, they acquire +1 charge. This is radical, so this is +1 charge. So Q in most cases is 1, in all cases almost, in electron ionization mass spectrometry. Q in most cases is 1, very rarely it comes below 1. Okay, what about the B squared? B is the strength of the magnetic field. Okay, strength of the magnetic field means that how strong a magnet is. Suppose a magnet, as I told you, and let me again recall that this magnet has the magnetic field. This is the B squared value. Okay, this is the strength of the it's the direction of the strength, and B squared will present its force. Okay, if B is 1 or 2 or 3, so it will be increased the force. The magnet will push the thing harder, the charge harder, and it will make the circle smaller. Okay, okay, these are things, and B, I suppose that it's a little bit clear to you. Now in this equation, things are like R is inversely proportional to the charge. R is inversely proportional to the field, and R is directly proportional to m, mass, and R is directly proportional to this potential difference. Okay, I'm going to explain each and everything, but stand a little bit calm. R. Now coming to the value of R and this magnetic field right now. Okay, if the magnetic field is small, big, if the magnetic field is big, as both things are inversely proportional to each other, like R is inversely proportional to, suppose no root is present, 1 by b squared. Okay, suppose, okay, let me write it like this. Suppose it is like this. Okay, so the more the magnetic field strength, the smaller will be the radius. This radius will be smaller. Okay, and the thing will be moving slower to the thing will be moving in a small circle, not in a big circle. A small b, if the b magnetic field is small, you have big circle. Okay, so how to connect it with these things? Suppose you have three particles, and let me write it like something big. Okay, I just want to write this circle. Okay, this is the circle, a little bit big. This is to detector, and this is from the ionization source. Okay, let me place some value. Suppose we have some magnetic field available. Okay, one is let's say you have some values of the magnetic field available, you can select them. One value is suppose 0.006 unit. Forget about unit, it's just a strength. Suppose it doesn't have unit like Gauss or Tesla. Okay, magnetic field strength. Okay, and another value is 0.01. Now it is big, very big. The third value is 0.02. This thing is twice than that. You have another value 0.03. Now suppose you have the choice to apply each value on the molecule. As I told you that the B squared, or the magnetic field strength, it is in inverse relation with the radius. Suppose you have a molecule, say 100, it has some molar mass and of 100, and you can say a molecular weight, suppose 100, and you want to bring it to the detector. These are suppose small windows, actually they are called slits. So as it enter here, and now your machine is operating on 0.06, and we should assume that, or we should suppose that this is very small magnetic field. Okay, very small magnetic field strength. It cannot deflect the molecule very much. So as you know that our molecule want to move in a straight direction, and this is the direction which is straight. Okay, this is, what is the molecule? It is positive radical, and we want to bring it here. Now it is moving upward, and these are walls. It's just like a game. Anything collides with the wall is destroyed. If anything comes to the detector, you detect it. Okay, this is detector. This is D for detector. Now you have this value, and suppose a little bit as it enter it a little bit deflects it, but still it collides here. So your molecule is destroyed. Now you increase you have a knob, and you just again came to the lab and injected the sample into the ionization source or the inlet system, and then it came to the ionization source, and it is bombarded by the electron and converted to a positive radical again. But now this time you increase the magnetic field strength to 0.01. Now this thing will be a little bit more deflected. Okay, now the curve path will be, okay, this is the old one. Let me write, okay, suppose this is the old one. Now the new one, it will start curving. Now you are using a good magnetic field, but unfortunately it collides here. Now suppose you increase the magnetic field to 0.02, and now this thing, okay, let me write it with some green bulb marker. Now it goes to the detector. How we do it. But again, let's say, now this is a magnetic, suppose you have, these are all just random values, okay. This is a value of 0.02 Tesla or something. Yeah, forget about the unit, because the blue one has a value of 0.01. Again 0.01. This black one, it is the same molecule. You perform 3 experiments. In the first experiment you used magnetic field strength of 0.006, very less. This is 0.006, and it is destroyed here. But as you increase the magnetic field, now the magnetic field curve it, but again it collide the wall with the wall, and game is over. You lost, you are failed, and you should restart the game. You cannot go to the other stage. But suddenly at 0.02 it went to the detector, and you, congratulations, you have done your second what is that game. You are in the second stage now. But this is for one molecule. But believe me, this thing doesn't work like this. I am doing it that you may understand the actual phenomenon. Okay, but this is easy. Suppose you increase the field more with this same molecule, okay, the molecule with 100 mass, you increase the field even to 0.03. What will happen? As you know that those things are inverse proportion. So as you increase the magnetic field, the radius will, when you increase it, the radius will become sharper. If you decrease this value, radius will be big. If you very much decrease, it will be like this. Okay, so suppose you decrease the magnetic field even further to 0.03. Now instead of colliding instead of going here, the green, this thing, it will move in this direction and will collide here. Suppose here or there, because small circle, it will require a small circle, and with a small magnetic field it should move in a big circle. Okay, this is one thing which right now I think that we have understood. Now another thing, here is mass. Oh, what to do with the mass? Mass appears again in the equation, and this thing is in direct relation with the radius r. Okay. Now let me erase this. We are not touching the V thing right now. We will touch it, believe me. Mass. Again, another thing, it is in direct relation. The bigger the mass, the bigger the circle. The bigger the mass, the bigger the circle. Okay, let me erase this. Okay, as you increase the magnetic field or rotating your knob, and it reaches to 0.02. Okay, suppose knob means button. Okay, this is button, and you just come here and 0.2. What will now happen? As you know that C and B are heavy. B will be destroyed somewhere here, and the C will be destroyed very near, okay, because as you know that the heavy thing, they will make big mass at some magnetic field than the smaller one, okay. If the heavy one will make big mass, okay, at constant magnetic field, and the smaller one, not of the heavy one, will make a big circle, huge circle with a huge radius, and the small one will make a small circle if the magnetic field is constant, okay. Suppose you come to 0.02 magnetic field, and now the 100 will pass very easily, and it will move to the detector. And suppose here I have tried draw some sort of spectrum. This is M over Z, this is increasing this way, and this is intensity or anything. So at 100, value 100, okay, this is M by Z, M over Z. At 100 you will observe a peak. Now again you increases the knob to 0.03, and as you know that from this example with the random values, what will happen, again all the three, now what will happen, you increases the magnetic field, one thing is for sure, this thing will be destroyed, and the B and the C, they will make some arc. The C will be make the arc over here, and the B may make a little bigger arc. Now if you increase the magnetic field to 0.04, suppose, what will happen, again something will happen. Now again, what will be the result? This A, it is the slight one, this is A, it will be destroyed here, okay, very near, even nearer than this. It will be deflected as it enter the field. Now the B, what here, where is the B? This B. So this one in the equations, or when we look to the mathematics, if 0.02 is good for 100, then 0.04 is good for the other one, the 200 one, okay. So the 200 one will, this will, B will move to the detector, and you will get a peak at 200. This is 200, okay. If this is small, this is 100. M by Z, M over Z, or M over Z. But what will happen to the C? C is heavier, so still it will not be deflected that much. It will come, and maybe it is like here, or it may be destroyed like here, or maybe earlier, because it's still heavier. Suppose it is destroyed here. Now if you and you will get B, this is B and this is A. Now you have still a little bit time remaining, suppose in 1 minute, and you increases the knob to 0.08, okay, 0.08. What will happen? Now again you have detected some molecules of A. Suppose when you are you increases, you were just rotating the knob, you just kept it for 0.2 seconds or 0.5 seconds or 0.8 seconds or 0.02, or just suppose you were rotating it, and it stood or remain fixed for 3 seconds on 0.02. So some molecules of A will enter, and if it focuses on the 0.04, okay, and it stayed for 3 or 4 seconds. At 3 or 4 seconds is very huge, but let's suppose we have now some molecule of the B went there. The A was destroyed and the C was destroyed, but the B went through, and now you came to the 0.08. Now what will happen? Now this is too much magnetic field for all of them, for A and B especially. A will be just destroyed here. Suppose here the B, because it's very big, so the B might be destroyed here. And what about the C? This is the C, and now the C might come through to the detector, and you will get a peak for a C to C, another peak for C. Okay, so you draw a spectrum within a 1 minute. But what happens in reality? Let me tell you what happens in the reality. Okay, in reality, the magnetic field, or the magnetic field, it is scanned. Scanned means that it is automatically changing very fastly. Okay, if you have some molecules, suppose you have these 3 molecules, and your magnetic field, suppose it is from 0.001, it's even smaller than this, to 1.0. Suppose these are some random value. Now the magnetic field will be scanning. Scanning means that it will be increasing or decreasing. Suppose you have 1 minute, maybe the magnetic field increases 100,000 times in 1 minute. It will be increasing or decreasing. So some of the now what will be happening if it is in scanning? So that is called the increase or decrease in the magnetic field will be called, they call it scanning. So it is scanning, or it is changing, okay, or it is fluctuating, moving up and down, increasing or decreasing. So what will happen? Because all the molecules will be here, so as you know that these molecules are moving extremely fast, even faster than bullet. Now, so when it is scanning in this thing, like this is scanning in point, suppose the whole time you have for the experiment is 1 minute, okay, and you start now, these are ionized and molecules went to the analyzer. Now first of all, 2 molecules will be destroyed and 1 will pass, okay, then the other 2 will be destroyed, the other 1 will be passed. So 1 molecule at a time will be passed when the magnetic field is, when its optimum magnetic field reaches, okay. So this show one thing, that the molecules the ions moves extremely fast, that the magnetic field, look at the magnetic field, it is increasing or decreasing, suppose 1 or 10,000 times in 1 minute, but still the molecules are very much fast. So the ions are so much faster that even they can match through to the detector. These ions are moving so much fast that this scanning time is slower for them, okay. So each one make through this to the detector, okay. Now it is one thing which we studied, but there are other things also. As I wrote this, R is equal to 2mv and b squared, okay. This is our equation. Something is missing, okay, yes, this is charge, okay. This is our equation now. So this, now another thing which we need to explain, that this is the voltage. So the voltage can also be varied, and we will discuss it in a other electric sector or double focusing mass analyzer, okay. It's just a magnetic sector. So now the conclusion is, this magnetic sector can work either by fluctuating or scanning the magnetic field, or this propeller potential, okay. The potential can also be changed, increase or decrease. It can operate when this thing is changing, so the magnetic field is kept constant, or if the magnetic field is changing, then this propeller voltage is kept constant, okay. So we'll now, this is a small demo of the magnetic sector analyzer, okay. The magnetic sector analyzer, it is okay, but it has, its resolution is not that good. What actually is resolution right now, we cannot discuss that very because the time is very short, and after some time we will discuss. But let me show you. Suppose you have a molecule which has 100,000 molecular weight, and the other has, suppose it has 1001 and it has 1000.2. You will see that how it could be like this. If these are two different molecules, if some machine is able to create such a magnetic field that it can separate both of them, okay, or record the spectrum of both of them, then it is high resolution.